So okay, so this slide is basically just restating what you guys already figured out now. So if Ashenfelter and Greenstone are overestimating the perceived risk here, then they're going to underestimate the VSL, which I think might explain perhaps the surprisingly low VSL. The other thing that I think is maybe particularly surprising and why I really think the VSL might be too low, like the VSL estimate that you get from the study might be too low, is that you can think about doing sort of a simple litmus test of how many years of travel time savings you're trading off for years of lives lost, right? Because I said that we want the denominator to be in dollars and then the numerator to be in dollars and the denominator to be in risk. But this is like kind of an interesting case where the denominator is initially measured in hours and like units of time because it's time savings, right? And then the numerator is measured in hours time. The denominator is also could be measured in terms of time savings in terms of like avoiding life years lost, right? So it turns out that in the typical traffic accident, like the typical person who dies is about I think 38 or 39 years old. And so if you look at life expectancy, you could infer that maybe they're losing about 40 years of 40 life years. So then when you take those like 5,000 lives that are lost, multiply by 40 years per life, you end up with essentially, in the denominator here, there's 200,000 or 207,500 years of life lost. And then the numerator here, remember I said there's something like 500 million hours of travel time savings. That turns out to be basically about 56,500 years of travel time savings. So like ironically, the travel time savings are not nearly as large as the life years lost, which you could write down a model where people would be able to, or where people would be willing to trade more than one life year lost on average for less than one year of travel time savings. But I think that model would have to involve some combination of first having like an extreme disutility of driving, and second of all having some sort of like basically not risk aversion, but like risk lovingness to yourself. So this I think really casts into doubt the idea that the lawmakers have actually figured out like the optimal trade-off here between risk and money. Okay, so overall, I think the study overall is nice, and just the effects of the estimate are useful, like the effects of speed limits on fatalities, and also seeing how much travel time changes. But I would probably interpret that particular VSL number with some caution. It does. I mean, I think the overall premise that lawmakers are at least doing some sort of like have some sort of trade-off in their mind between fatality effects and travel time savings does make sense, even though it's perhaps not. Like they're not necessarily choosing what they think is the optimal number for society. They're probably choosing something more like what they think is going to be politically popular. But again, it's unclear what numbers they actually have in their head when they're making these choices. And if you believe the results, or even if you believe that the results are overstated by a substantial margin but still are not zero, you could kind of conclude there's actually like almost a free lunch here. That it turns out that lower speed limits to 55 miles an hour. So we thought that the trade-off was essentially better fuel economy, so like fuel savings on the positive side, but then more travel time on the negative side, and that is true. But then after you take into account the life years lost and sort of subtract that off from the travel time, the net change in travel time is actually basically negative. So like if you sort of sum up all of the life years lost plus travel time, that's actually lower under the 55 mile an hour regime than it was under the 65 mile an hour regime. Like we're actually saving time from that. So you could actually think that it's like a free lunch. Now that being said, almost nobody drives 55 miles an hour on the highway, as you can see, if there's a limit of 65 miles an hour. And part of that it may be related to just the fact that you don't want to be you don't want to be driving a very different speed than the other cars. But I think probably even if there were no cars around, most people would choose to drive faster than 55 miles an hour. So there's like I think there's a couple. So the question is, well, if it's a free lunch, then why aren't people taking it? And I think part of the answer comes down to like externalities, right? I mean, there's a difference between saying that if everybody drives at 55 miles an hour, then everybody will be safer, and saying that if I drive at 55 miles an hour, then I will accrue all of the safety benefits of doing that, right? Because not only so I'll accrue some of the safety benefits, but there will also be safety benefits for people who I might crash into when I'm driving, and when I'm driving slow, they probably prefer to have an accident with me than if I'm driving very fast. So just because as a whole society might choose to set a speed limit, doesn't mean that each individual person wants to necessarily drive at that lower speed. So there's an externality issue there. Okay. So then the next paper that we'll talk about here, I don't think we'll quite finish today, but that paper is basically it's by Lucas Davis, who is he's a economist here at UC Berkeley in Haas, and he has this nice paper that basically estimates the value of a statistical case of childhood leukemia. And the idea is that there's this cancer cluster that appears in this particular county in Nevada, and what he wants to do is see how much housing prices fall when that cancer cluster appears. So basically, how much do you have to give people to induce them to stay in or to move into this place that seems to have some sort of like cancer risk associated with it. So this is again a revealed preferences approach. You're looking at how households trade off housing prices and perceived leukemia risk. And there's a non-market good here, which is this leukemia risk, which is bundled with a market transaction, which is the housing transaction. So what he does, he leverages this sudden appearance of a leukemia cluster in Nevada. And this cluster is located in Churchill County, Nevada, which I'll show you a map of in a little bit. So it turns out this is a pretty small county. It only has a population of 24,000. It makes it something like a fifth the size of the city of Berkeley in terms of population. But I mean, Nevada basically has no people living in it other than in Las Vegas and Reno, so it's not a big surprise. And nor is it a surprise that nobody want to live there since it's all a desert with some radioactive waste probably mixed in there. And so pre-1997, there's no historical record of childhood leukemia in this particular county. And then from 1997 to 2001, you have basically 15 leukemia cases in this population of 24,000 when you'd expect one. So remember, I mean, even though it's an entire county, this is like basically a small town. Like this population is not much bigger than Reno, which is just over the hill here. So if there are 15 leukemia cases in like 4 years in that type of population, people will start talking about it and see what's going on. And in particular, it becomes publicized in 2000 when like newspapers publish a bunch of articles, local newspapers publish a bunch of articles about it, and everybody becomes aware of it. And the Nevada Health Department and the CDC investigate, but can't really find any reason why cancer rates should be elevated. So that this fact, I don't know whether you sort of interpret that as being good or bad. So the good interpretation, if you were living there, would be like, well, they looked around, they couldn't find anything that would be an obvious source of it, so maybe it's just really random noise, even though 15 times the expected rate doesn't really sound like random noise. So that would be kind of the positive spin, and the negative spin would be like, oh my God, there's something going on, I don't even know what it is. Like, we need to get the heck out of here. So at any rate, what happens, or what he does, is he applies this differences research design. So he has something, that's changing over time, which is this leukemia risk. He wants to look at its effect on housing prices, but we know that he needs to find some sort of control group to basically compare the change in housing prices against. And so his control county which he's going to use to compare the treated county to, is this nearby adjacent county, which is Lyon County. It also has a relatively low population, 35,000 people, and it lies directly west of Churchill County. So in the map here, I've highlighted Churchill County first, which is the county that has the cancer cluster. So like Vegas is somewhere down here, and then Reno is like right near where the angle occurs there. So these are further east of Reno. And then Lyon County, which is the control county, you can see lies just directly west of Churchill County, which is the county that's getting all these leukemia cases. So Lyon doesn't have a spike in leukemia cases. And the diff design is then going to compare the changes in property values in Churchill County, which we're viewing as the treated county, to changes in property values in Lyon County, which is the control county, to see basically how much property values change in response to this cancer cluster appearing. So YT1 minus YT0 is basically going to be the change in property values in Churchill, and then YC1 minus YC0 is going to be the change in property values in Lyon County. And he has to, of course, basically define two periods, a pre-policy period and a post-policy period, a pre-treatment period and a post-treatment period. So the post-treatment period, period 1, he sets as being 2000 to 2002 because the cluster becomes publicized in 2000. And then the pre-treatment period, he sets as being 1990 to 1999 because that's before there's sort of any widespread knowledge of this cancer cluster. And the question that you're always going to have in your mind is, when you're evaluating the study, is whether or not this adjacent county, Lyon County, is an adequate control for Churchill County. So does it give us a good sense of what would have happened to housing prices in Churchill County had there not been this cancer cluster appearing? And since he actually has this long period of data on housing prices proceeding when the cluster appears, he can actually show you some pretty convincing evidence of that. So he has this figure, which I've reproduced here, which really suggests that Lyon County is a pretty good control or counterfactual for Churchill County. So there's three series on here. One, which is the line that I guess has circles in it, is Churchill County housing prices. So this is data that's taken basically from like the federal government and I guess maybe from the county registrars as well. But what they're doing, what he's plotting is basically a housing price index over time from 1990 to 2002 for each of these counties. And so for Churchill County, you can see it's trending upwards. But in 1998, it's the line that starts to diverge and basically goes down when the other two continue going up. So, or I guess it's about 1999 that happens. So that's the point at which the cancer cluster is appearing. Lyon County is this comparison county. It's the series that has the triangles in it, and you can see it's basically just going up continuously over time here, trending upwards. And then the state of Nevada, so basically property prices for the entire state of Nevada are given by this third series, which is the series that I think has the square in it on the bottom there. And you can see that that actually tracks Lyon County pretty well, and it also tracks Churchill County. In fact, it arguably tracks Churchill County even better than Lyon County does in the pre-period from about 1990 to about 1999. So the fact that those series are all pretty close to each other before this cancer cluster appears gives you some confidence that essentially whatever trends might be affecting or whatever shocks might be affecting Churchill County other than this leukemia cluster probably also are going to affect Lyon County and even just sort of the overall market of Nevada. And then you see this notable drop in the housing prices in Churchill County in 2000, and that's evidence that, in fact, this cancer cluster is having a noticeable drag on housing prices there. So the diffs and dits estimates confirm what you can probably already see in that figure. So basically, in Churchill, the average price, I think it's actually the log of average prices in the 1990 to 1999 period, so this is pre the cancer cluster, is 11.587. In the post-cancer cluster period from 2000 to 2002, it drops to 11.55. Then in Lyon County, in the pre-period, it's 11.627, and in the post-period, it continues to increase to 11.667. So if you write out our diffs in this formula and basically calculate the change in Churchill, subtract off the change in prices in Lyon, you'll get minus 0.037. So remember, this isn't log, so you can interpret the differences as being approximately like percentage point changes. So this is or percent changes. So this is saying that Churchill County prices dropped 3.7% approximately after the cancer cluster appeared, and Lyon County prices actually increased by 4%, and we're going to subtract that off because we take the change in the differences. So once you take those two numbers and difference them, you get 7.7%, 7% decline. So what that's telling you is basically that relative to this control county, Churchill County experienced a 7.7% drop in its housing prices after the cancer cluster became publicized. However, there's a caveat here, which is, remember, so in order for the diffs and dits estimator to give you an unbiased estimate, it has to be the case that whatever changes are occurring in the treated county other than this treatment also need to be affecting the control county. And it turns out that if you look at the actual data, so he has microdata not only on the price at which the house was sold, but he also knows some of the characteristics. So he knows things like the number of bedrooms and the square footage of the house and so forth, right? And so when he looks at those data, he actually finds that the composition of houses that are sold in Churchill County also changes during this period. So basically when the cancer cluster, around when the cancer cluster is publicized. And what he finds is that essentially after the cancer cluster gets publicized, the houses that are being sold in Churchill County tend to be larger, and they tend to be larger lots, and they also tend to have more square footage in the house itself. So what this is saying is that basically not only do the prices people, not only were the prices people willing to pay, not only do those change, but also sort of the types of houses that people were willing to buy also changed. And so that's actually introducing, I guess you could think of it as some sort of bias into his estimate, right? And in particular, what it's saying is that this 7.7% number is actually too small, right? So Churchill County is the county that gets the leukemia cluster. And it turns out not only do prices go down there, but the houses that are being sold are actually larger than they were before. So it's not that, I don't think you want to think of this as being like suddenly they constructed a whole new stock of houses that are bigger than they used to be. I doubt that the housing stock itself is changing all that much over just a 2 or 3 year period. I think what's happening is that basically in any given year, only a small fraction of houses are being bought or sold. And it turns out that the types of houses being sold in Churchill after the cancer cluster becomes apparent are these larger houses. And you can think of it as sort of being two sides of the same coin, right? So you have this cancer cluster, all other things being equal, people aren't going to want to buy houses in that cluster. So you have to induce them to buy in order to actually have any sales. One thing you're going to do is you're going to reduce prices, so you see that 7.7% reduction. The other thing you might do is basically observe that only these larger houses that are sort of more attractive based on the house itself are going to sell because people also value that, and so that may help induce them into buying there. So since the houses being sold are getting larger, what that says is that actually, if there hadn't been a cancer cluster, we would have expected the prices in Churchill County to outpace the prices in Lyon County, right? Because the stock of houses being sold or the types of houses being sold are actually becoming more attractive. So what he does is he sets up a linear regression, and he controls for house size and actually a bunch of other control variables as well. So recall again that we said that running regression that includes basically a cross-sectional indicator, which is the county indicator, and a time indicator, which is this post-2000 indicator, is equivalent to doing a diffs and diffs. So you're basically regressing housing prices on the post-2000 indicator interacted with being in the cancer cluster county. Then you're also controlling for being in the cancer cluster county, which is that Churchill C variable, and then you're controlling for being in the post-2000 period, which is that post-00 variable. Okay, so let me stop here. But basically, just to preview the result, what he finds is that once he controls for like lot size and other things, the effect becomes even larger. I think it approximately doubles. The effect of the cancer cluster on housing prices. So it was like 7, yeah. So instead of like a 7.7% drop, it's like a 15% drop or something like that.